This lesson is on the fundamental theorem of calculus, part 1. The basic idea here, before I make it formal, is if I have g of x equals the antiderivative of f of x, drawn like that, then basically I have a relationship between g and f. G is an antiderivative of f, and f is the derivative of g. So this simple statement here gives us a relationship. It gives us that g is an antiderivative of f, and f is the derivative of g. Now, to make the theorem formal, we'll say if f of x is continuous on some closed interval a to b, and see, I'm going to define g of x to be a little bit differently than I did before. I'm going to say g of x is the integral from a to x. And then because x is in the bound, I have to use a dummy variable, f of t dt. This is essentially what we just showed with a little bit more fancy notation. And let's suppose that this is true for x belonging to the interval. So, like we showed before, if we define that function, then the relationship is defined. So I will say then g of x is an antiderivative of f of x. The real variable is x. But also, we want to say that f of x is the derivative of g of x. i.e., to say that differently, g prime of x equals f of x. This is like a therefore. The fundamental theorem of calculus, part 1. What I'm asking you to do is, if you see this relationship defined on your paper, then automatically you know that g prime is equal to f. If you recall, the derivative of an integral is just the integrand. Let's think of it like this. If I said g prime of x, well, then that would equal the derivative with respect to x of the integral from a to x, f of t dt. And then we have the derivative of the integral gives us the integrand. But I'm going to extend this now. I'm going to say, what happens if we do g prime of u of x? Well, it's still the derivative with respect to x of the integral from a to u of x this time, f of t dt. And this is where it gets a little bit different. It's going to be f of u for f of u of x, so f of u, but then we need times du dx. That's the chain rule portion. Chain rule. To start off, we're going to look at ones we just do. You're going to accept something at first, and I actually hope you get a little bit irritated. I hope you have the feeling that's easy to do. I can do 1,000 of them, but I'm a little bit irritated about something. That's the goal here. Number 1, I want you to find the derivative with respect to x of the integral. Now I want you to think of any number. Okay, I just heard 3. Good choice. And we're going to go the derivative with respect to x from 3 to x of some function e to the negative t squared dt. Easy enough. We just have to do it. The derivative of the integral is the integrand, except we get rid of the dummy variable in place of its real variable. So the answer is e to the negative x squared. Very simple, yes? Number 2. we're going to find the derivative with respect to x. Okay, pick a number, any number, good, -1. This time it's not going to be x, it's going to be a function of x, it's going to be 5x. Same integrand, e to the negative t squared dt. This time we're just going to do it. So above it tells us we're going to take the 5x and plug it in for t. Looks like that. But then by the chain rule, I have to multiply by 5. Number 3. We're going to find the derivative with respect to x of the integral from x squared to, pick a number, 3. E to the negative t squared dt. What I'd like you to see here is, because the variable is in the bottom bound, I want to transform it into the upper bound, but in doing that I have to make it negative. So this is going to be negative derivative with respect to x, flipping the integral, 3 to x squared e to the negative t squared dt. So we have a negative out front, then it's e to the negative x squared gets replaced for t. Then we need the chain rule, so times 2x. You see, this 2x was the derivative of this bound, which was a function of x. So now, back to your irritation. A couple things that people are irritated about or need clarification about. How come I can pick any constant here and it doesn't matter, it doesn't influence the answer? See, I picked 3, and then I picked -1. I also picked 3 again here, and it didn't matter what we picked for those constant bounds. The answer is independent of it. That's one point that people want to be irritated about. They need clarification. The other point is, what do you really mean about this chain rule? Why does that really come into play? So that gives us motivation to talk about the next couple examples, which are ones we can verify. I hope doing the ones we can verify will answer the 2 points of concern or irritation. Number 1, I want to find the derivative with respect to x of the integral, I'll pick a number, 2, to a variable x of an integrand t squared dt. First, I'm just going to do it like I did in the examples before. I'm just going to do it. The answer is going to be x squared. But now we're going to verify this. So what do I mean by that? I'm actually going to run through all the mathematical processes. Okay, so I'll rewrite it. And I keep the derivative with respect to x outside. But then I'm going to use the fundamental theorem of calculus part 2 to do this part. And in doing that, I find the antiderivative of t squared, which is t to the power of 3 over 3. And I'll take that from 2 to x. This derivative with respect to x is still out front. I'm going to plug in the x first, x cubed over 3, minus, now I'm going to plug in the 2, and that's going to give me 8 over 3. Now, the last thing I need to do is take the derivative of this new quantity. Notice that the derivative of this constant will be 0, and so the final derivative of this expression will be 3x squared over 3, or simply x squared. Cha-ching! Cha-ching! It checks out, it verifies. Do you see now why it doesn't matter what I chose here for 2? Suppose I chose 12. 12 would have carried here, 12 would have carried here, 12 would have given me a much larger numerator, but it wouldn't matter because the derivative of that constant would also come out to be 0. So the fact that I'm taking the derivative as a last process, it takes care of any constants which the constant in the bound provides. Let's take a look at the second example. The derivative with respect to x of the integral from 1 to x squared cosine t dt. The first thing I'm going to do, and you should do also, is just do it. So I replace the t with x squared, and then with the chain rule I need times 2x. Now I'm going to actually run through the process and rewrite it first. Okie dokie. Keep the derivative out front. I'm going to find the antiderivative of cosine t, which is sine t, and I'm going to take that from 1 to x squared. So keeping the derivative outside again, I'll have the sine of x squared minus the sine of 1, which is a constant. Now I'm going to take the derivative of that expression, and that will be cosine x squared times the derivative of the stuff for chain rule times 2x. It verifies. And hopefully that explains why when this bound is something other than just x alone, we need to take its derivative at the end for chain rule. I would also like to comment that the goal will be to get the answer. The goal will be to, so to speak, just do it. That's what we want. I won't ask you to do it and verify. The verification process is simply that you understand why it works. In the case above, this particular integral is not integrable. You can't find the antiderivative. You're not able to verify it. But in theory, the derivative of the antiderivative would be itself. So the goal is just do it. The notes were to explain why it works.